minutes to spare today. But that's better than missing it completely, I guess, which I was worried I was going to have to. So I was able to be here for most of it. And it'll be much the same tomorrow. I have to skip out about 20 minutes early tomorrow, but I didn't want to miss the whole thing. So yesterday we started talking about trends in the periodic table and what it can teach us. So what are some trends in the periodic table? What can it teach us? Yeah.
That you know how many electrons are on each shell from going left to right.
Good. So if we look at nitrogen, we can tell how many electrons are in, not specifically which shell. It's outermost shell. Did I remember the word we used for that, by the way? We're going to talk about it more today. Yeah, the valence shell. So nitrogen, we can just count over. 1, 2, 3, 4, 5. And we know that nitrogen must have 5 electrons in its valence shell. Good. That's something we can learn just looking at the periodic table. We count over left to right, tells us how many electrons in the valence shell. What else? What else do we know? Yeah.
That in the groups, all the elements that are in those groups are all related to each other.
Good. That's right. So there's a chemical relationship because we're going to learn that chemical reactions have a lot to do with electrons. And so as it happens, all those group 1 elements that have 1 electron in the valence shell have similar chemical behavior. So they're very reactive. All the group 2 elements have similar chemical behavior. Less reactive than group 1, but still quite reactive. All the group 7 elements have similar chemical behavior. They're really reactive too. 17, I should say. Group 18, what do we call them again? Remember the lovely name? Noble gases, right. And what's their chemical behavior like? You hit the nail on the head yesterday. I'm pretty sure you told me how they were going to behave, the far right ones. I think you did, though. I could be making that up. Sometimes I make things up, but that's my memory. Anyway, how do they behave? Those ones on the far right. Noble gases. Yeah, they're very unreactive. They have no desire to gain or lose an electron because they already have a full shell. And that's what we're going to talk more about today. That means they're nice and stable. Full shell equals stability. All right, then we talked about specific trends about the atoms themselves. And the first topic we talked about was, that's about what? Not ions. We talked about radius, atomic radius. First of all, what's meant by atomic radius? What's that mean? Very good. Yeah, the size. Obviously a bigger radius, because we think of an atom as being basically what shape? Yeah, what's a 3-dimensional circle? A sphere. Good. Yeah. We think of them as basically being a central nucleus surrounded by these electrons, and we think of that as being basically spherical in shape. Which is good because next year your mind will be totally blown when you see what the actual shapes of these things are. It's crazy. But yeah, we think of them basically as spherical, basically as having a radius. And how does that trend work on the periodic table? How's that work? What can I know about the size of an atom just looking at the table? Yeah.
As we go down the table, and you see that we have a size.
Good. So as we go down the table, so if I pick any one group, say I pick group 14, carbon is going to be smaller than silicon, it's going to be smaller than uranium, smaller than tin, smaller than lead. I don't know what that's called, but you get the idea. Yeah, I'm pretty sure it's called. Why? Why is that the case?
Because there's more electrons in it.
Sure, more electrons. Specifically, there's more shells. Right? They have to form new orbitals. Every time we go down a group, we get a new orbital, and a new orbital exists outside the previous one. Right? So if this orbital is here, the second orbital is here. Right? Not unlike if we discovered that our solar system had another planet further out than the current one, we would now think our solar system is being bigger than we thought it was before. Right? You add a new orbital, things get bigger. Does that kind of make sense? I think that one's very intuitive, right? As we go down the table, we get more shells, the atoms get bigger and bigger. Common sense, right? What's the second trend on the periodic table to do with the radius of these things? mass number or something. It's so serious. So, I can see you want to do the mass number. Yeah, cool. All right, so come on, what's the other people who have been silent thus far, or thusly, as I might say? What happens is we go left to right to the size of that. Yeah, they get smaller. And that, to me at least, isn't intuitive. Because as we go across the table, we have more electrons, right? You would think that it would get bigger. Why does it get smaller? Why?
Because the nucleus is bigger and it is from the pole as it is from the sun.
Yeah. So within the same shell, as the nucleus gets bigger, we have more protons. Protons have that positive charge. And so as the nucleus has more and more positive charges, those negatively charged electrons are more attracted to the nucleus, right? There's more of a positive charge in there, so they get pulled in tighter. So within a single period, within a single row, let's say period 4, potassium, calcium, scandium, titanium, so on and so forth. What is the biggest atom that's in period 4? The largest atom in period 4. Yeah. Potassium. Good. Because it's got 4 shells, but because relative to everything else in period 4, it has a small nucleus with a small positive charge. It only has 19 protons, whereas something as big as krypton has 36. Those electrons aren't pulled in as tightly, so they're able to float freely further away. And obviously, in period 4, the smallest atom would be krypton, right? Because it now has also 4 shells, but it now has 36 protons in its nucleus. So it's able to pull those electrons in really close, really tight. Do those trends make sense? Because all the other trends really make sense based on that. If you understand the size of these things, then we can talk about the other trends. So the next trend we talked about was ionization energy. What's ionization energy?
The energy needed to display an electron or to give an electron to an atom.
Not both. It's one of those two. Which is it? Good. And that's the key. Ionization energy only involves taking away an electron. We'll talk about giving electron. That happens with the next one. But the name given to the energy required to take away an electron, we call ionization energy. And you can think of it this way. If we start off with an atom, we want to take an electron away from it. So we end up with that electron by itself. First of all, once the atom has lost an electron, what will we call it? Yeah, we'll call it an ion. And if it's lost an electron, what kind of charge will it have? Say? Yeah, which one? Positive. Okay, you won't speak, but I'm seeing hand signals. That's good. That's a start. Yeah, it'll have a positive charge, because if you lose a negative, that's going to make you positive, right? You now have more protons than electrons. But to make that happen, to snatch an electron away, what do we have to do? Yeah, we have to give it energy. And specifically, we have to give it what we call ionization. Yeah, I can spell. Good. Now, on the periodic table, it's really simple because this trend is the opposite of size. Think of it this way. A really small atom keeps its electrons close, right? In that case, how easy is it to steal those electrons? Yeah, it's very hard, right? So your smallest element, what is the smallest element again? Helium. It has its only 2 electrons really, really close to its nucleus. Is it going to be easy to take those away? No. So it has a really high ionization energy. If size is low, ionization energy is sky high. Does that make sense? On the other hand, what's the smallest? What's the biggest atom on the periodic table? Francium. Good. Francium has its electrons way, way, way far from the nucleus. What's its ionization energy going to be like? Very small. Does that make sense? It takes very little energy to steal an electron from francium. And you're going to see that this is the trend. If you understand how size works, all of these other things we work are just the opposite of that. All right, so for ionization energy, a low size, high ionization energy. Right? A big size, low ionization energy. Easy to steal an electron. from an atom when its electrons are way, 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 way far away from the nucleus. Questions about that one? All right, and that led us to our next trend. Oh, there we are. Electron affinity. And electron affinity is the same idea, but in reverse. If you have to give an atom energy to take an electron away, what happens if you give an atom an electron? It gives you energy. Reactions that give off energy, and you know this, what kind of energy does a reaction give off, typically? Yeah, mostly, and what's thermal mean? That was very sciencey. Which is good, we're in science class. Heat, yeah. A lot of reactions, you can feel them give off heat, right? You burn gasoline, it gives off heat. The heat that it's giving off is really this energy. It is the electron affinity. It's that as some of those atoms are gaining electrons, that releases energy. Does that make sense? So we call this electron affinity. I really do loathe that name because to me, there's nothing in that name to tell me what it is. I would love if it was called like negative ionization energy or something. I don't know, but that's not. They call it electron affinity. But again, it's the same idea. You can imagine that a really small atom that only has a couple electrons to begin with, and that keeps its electrons really close, as we put another electron in there, it's going to make a big difference, right? And how much energy would it release? Tons and tons of energy. On the other hand, is something really, really huge like francium going to get very excited by the addition of one more electron when it already has 87? No. So just like ionization energy, this is the exact opposite of the size trend. Does that make sense? Small atoms, big electron affinity. Big atoms, small electron affinity. Does that basically make sense? Any questions about that? Okay. The last thing we're going to talk about today then, or from yesterday's note, which is going to lead us in today, is this idea of electronegativity. Electronegativity. All right, so this is the last periodic trend. And electronegativity is related to the other two. In fact, it's specifically related to electron affinity because it's a measure. It's not energy, all right? This is not an energy measurement. Rather, it is a measure of an atom's pull on electrons. The technical term would be it's a measure of an atom's tendency to gain electrons. But really, electronegativity is in the fight for electrons, and atoms are constantly fighting over electrons. Electronegativity is how strong that atom is. Does that make sense? You know, you can imagine if, like today, I forgot to get a coffee, and I see Zach Brown come in with his coffee, and I want his coffee, we're going to fight over it. And Zach's going to have a problem because I'm very strong and Zach is much less strong. So I'm going to get his coffee. Then I'm going to drink it right in front of him. And that's just the way the world works, right? Now, if Zach and I were both atoms and the coffee is an electron, I'm more electronegative. Does that make sense? Electronegativity is just how strong an atom's pull on electrons is, all right? Okay, that's obviously very casual language, but it makes sense, right? And again, the trend is just what we've seen in other trends, which is that the smaller the atom, the bigger its pull. Does that make sense? The smaller the atom, the bigger its pull on electrons. So I've seen this taught a lot of different ways. I've had it taught to me in a few different ways. And the one that stuck with me was this, where if you can figure out how big an atom is, all the other trends we talked about, ionization energy, electron affinity, and electronegativity, are just the opposite trend. Because a smaller atom is always more electronegative, it has a higher ionization energy, it has a higher electron affinity. Small size is big everything else. Big size is small everything else. And that's, again, does that work atom for atom for atom for atom every time? No. But it's the general trend on the table. Does that make sense? And if you look, we put this graph down here. You can see there's some hiccups in the graph in places like this. But in general, it follows the size trend, right? Which is each period, it starts low and gets higher and higher. Any questions about that? Yeah.
How would you feel if you had a one that has a
I will never ask you to. And here's what I mean by that. There's a reason we have a periodic table. We can look and get the exact numbers. A more detailed periodic table, which I'm going to give you at the end of this unit, once we want to start actually using the numbers. First, I want to know the trends. So I'm not giving you a detailed periodic table yet with all the numbers in it, because I want us to just think in terms of trends. Does that make sense? At the end of the unit, I'll give you one with numbers. And if you need to know the electronegativity, you can go look at the actual number. So do I expect you to memorize that gallium is a real exception, and it's lower than it would be based on its trend? No, I don't know. But I want you to understand the trend in general. Does that make sense? Because the big thing in this course is going to be understanding how and why chemical reactions work. And the big thing that we're going to learn is that chemical reactions all are about electrons moving from one place to another. That's what a chemical reaction is. It's electrons doing crazy things. Does that make sense? And these trends will help us understand in general how they work. Was that a reasonable answer to your question? Does anyone else have a question? Now is a good time to ask them. Yeah.
When the first of the thing goes from lithium to to what?
Yep.
Are those little dots?
Those are all the little dots. That's right. See on there is helium, neon, argon, krypton, xenon, and radon, because they are so non-reactive that they don't want to lose electrons, they don't want to gain them. They don't want to steal them from other people, but they won't give them up. So we generally don't think about them when we think about these trends, because they just basically don't apply. For all intents and purposes, everything in group 18 just doesn't react. But yeah, each little dot is the next atom in that alone. Does that make sense?
Yeah.
They just didn't put every letter on it just because it would be a lot of letters. Deep, right? Great question, by the way. Any other questions? Yeah.
So that hydrogen is not part of
Any sort of trend, yeah. Hydrogen's a really interesting case. Hydrogen is part of group 1, and its behavior is kind of like group 1, but it actually sits in this weird middle place, where it usually will give up an electron and become a positive ion, but sometimes it actually, in certain situations, will take an electron and become a negative ion. Hydrogen is a really, really interesting element. It has a lot of interesting behaviors. And you're going to find that early on in this unit, I never use it in any of my examples. And in the second half of this unit, we're going to talk about it a lot because it's all the special cases. Does that make sense? And you see that right there because it really doesn't fit with the rest of the trend, right? Great questions. Any others? All right, do we feel good about that? We're going to talk about size, ionization energy, electron affinity, and electronegativity every day for about the next week, just for 2 or 3 minutes. I'm just going to quiz you and like not written quiz, but point and thought, just to make sure we're making sense of those trends. Does that make sense? All right. Electronegativity leads us right into, are you kidding me? No, do you guys know about the staple and group feature on the photocopier?
Yeah.
This is Satan's idea of a practical joke. One of the options on the photocopier is that you can send a document to it and have it staple all of your page 1s together in one big stack, and then staple all of your page 2s together in one big stack. This is called the staple and group option, and it's right under staple and collate which is what you would normally think of doing, which is make a copy, staple it, make a copy, staple it. Obviously this morning, without realizing it, and so now I have a large stack of page 1s that were all stapled together, and a large stack of page 2s that were all stapled together. Would you mind handing out a page 1 to everyone? And would you mind handing out a page 2 to everyone? I'm sorry about that. Okay. What's that? Don't worry about it. You know, I said I'm going to quiz and remind all week. Okay. But, focus. Thank you very much. Thank you. Okay. Today's lesson and tomorrow's lesson aren't even actually in the curriculum. It's assumed that you know it from grade 10. My experience has been that a lot of time passes between grade 10 and this class, and sometimes it's good to go back and review it, which is to say this. The skills that we're going to talk about today and tomorrow, you're going to use every day in this course. So if we have to spend 3 or 4 days on it, we'll spend 3 or 4 days on it. You have to have this down, and I'm willing to spend a bit of time to make sure you have it really, really well. Does that make sense? So I want you to communicate with me, actually, or tell me like, yeah, I remember this, I've got it, we're good, we can move on, or hey, you know what? I need to slow down and maybe relearn that, maybe refresh myself, whatever. Just keep in communication with me, okay? Because this won't go away. So don't think that you can just like, okay, I'll suffer for this through 2 days and then I don't have to think about it. You're gonna have to know how to come up with the formulas of ionic compounds every day between now and February. So we want to just be breezy and easy. And eventually it will be, I promise. It's just like any other skill, you develop it by just repetition, right? You want to play that C major scale, you just play it 1,000 times, right? You want to make those free throws 90% of the time, you just sit there and do 1,000 free throws. In my case, I've eaten a lot of bacon and I'm good at it. So, let's see why you're laughing. All right, so we said electronegativity is a measure of what? I like to move around, maybe you guys will like get excited. Electronegativity is a measure of what? Just talked about it. Yeah. That's right. Electronegativity is how strongly an atom pulls on electrons. The higher the electronegativity, the more it will pull on electrons, and a strong atom will be able to pull them right away from a weak atom. And that's what we're going to talk about here. So electronegativity, recall, as if we didn't talk about like 2 seconds ago, recall that electronegativity is a measure of an atom's pull on new electrons. The higher the electronegativity, and of course we should have an apostrophe there, that was lazy writing, the higher the tendency of that atom to gain electrons. And as a rule of thumb, I want to compare metals and nonmetals. So first of all, on what side of the periodic table do we find the metals? Yeah. Yeah. They're on the left, and they go all the way to here, and this line separates metals from nonmetals, right? And they usually call this span that touches that line the metalloids. Does that ring a bell? You talked about that lots in grade 9. Maybe you talked about grade 10 again. But yeah, so the metals are the left side of the periodic table. And obviously the nonmetals are the right side of the periodic table. So, you remember yesterday we said that just by counting over how far, we can look at how many electrons these things have in their outer shell, right? Well, say hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, all those group 1 metals, well, hydrogen's not a metal, but all the other ones, how many electrons do they have in their outer shell in group 1?
Around 1 or 2.
Not around, specifically, if they're in group 1.
About like
Oh, no, good, like metals in general, sure. But group 1 has
One.
One. Group 2 has 2. Now, if the goal of an atom, and we're going to talk about this, is to have, what does an atom always want to have? What's its goal? Good. They want to have a full valence shell. And you can think of it like this. Anyone ever had the tires, new tires put on and they don't balance the tires and you get in your car and the steering wheel just shakes like crazy? You guys are early in your driving stage. But with a tire, which is something that spins around a lot, they have to put little metal tabs on the side of it and make sure that the weight is distributed evenly. If they don't, it'll shake like crazy, which damages the tire, can damage your front end, and is very uncomfortable to drive. It's noisy and it shakes a lot. Does that make sense? And just small differences can do it. They add little tiny weights, but it needs to be perfectly balanced. Well, electron shells have electrons spinning around the center atom very, 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 very quickly. And just like your tire, if they don't have the proper equal distribution of them, the thing is very unstable and it flies apart. Does that make sense? It has to have the right number of electrons. And a full shell happens to be that right number of electrons. That makes sense? Now, when we look at the metals, like lithium, beryllium, or sodium, magnesium, these over here, is it going to be easier for them to gain enough electrons to have a full shell? In the case of lithium, it would have to gain 1, 2, 3, 4, 5, 6, 7 electrons to have a full shell. Is it going to try to gain 7 electrons, or is it easier for it to just get rid of the one it has? Good. Does that make sense? So for metals, they tend to have just a few electrons in their outer shell. So few electrons, and you will see me use this symbol all the time. Maybe you want to make a note. Maybe you've seen it before. If I put E negative, I mean electron. So it has just a few electrons in its valence shell, so it tends to lose them. Nonmetals, on the other hand, the right side of the table, they don't lose electrons. They tend to, they tend to gain electrons. When they lose an electron, what charge will a metal end up taking when it becomes an ion, if it's losing electrons? What kind of charge? Yeah, good. So they make positively charged ions. And does anyone remember the word, the name we give to a positively charged ion? I bet you learned it. Maybe you didn't. It's possible you didn't. But I bet you did. Does this look familiar? Cation? Not caution. Though it does look like caution, doesn't it? But be cautious, because it's actually cation. Haha. What a pun.
The nonmetals still lead.
There you go. Now, on the other hand, nonmetals, they tend to gain electrons. So what charge will they tend to take? Yeah, if you're getting more electrons, you're getting more negative charges. So you're going to have negatively charged ions. And what do we call a negatively charged ion? Very good. Very good. And the last thing I'm going to put on there is we can think of it this way. The metals have low electronegativity. The reason this happens, electronegativity. Goodness, that's a long word. And it is that lack of strong pull on electrons that means that they're going to lose them. Does that make sense? They don't have a strong pull on electrons, so they tend to lose them. Nonmetals, on the other hand, have high electronegativity. Good. I am genuinely astonished how long this word is. Electronegativity. Wow. I could, but now I'm committed. And it's a sense of accomplishment. I feel like I've really done something useful here. Questions about that? Okay. So, stability. We've already talked about this, but atoms are only stable if their outer shell, which of course we call what again? Yeah, the valence, is full. This is why they form ions. And I gave you a little table down here of all of the ions that are consistent. You're going to learn that some of the metals in the middle, I mean, in grade 10, you should have already learned, but if you didn't, we're going to talk about it a lot again today. The metals in the middle can do interesting and complicated things. They can form more than one possible ion that's stable. But all of these ones that I've shown here, everything in group 1 and 2, everything in group 1 has how many electrons in its outer shell? So how many electrons does it have to lose? It's 1. So what charge is it always going to take?
Positive 1.
Positive 1. Everything in group 2 has 2 electrons to lose. So all it can lose is 2. So it'll always take a charge of plus 2. It gets messy in here. But there are some that are consistent. Silver, cadmium, zinc, aluminum, gallium. They form ions consistently. The rest we'll talk about tomorrow. But then the nonmetals here. Everything in group 17 is 1 electron away from a full shell. So how many electrons will they get? Just 1. So what charge will they take? Negative 1. So they will always take a negative 1 charge. Oxygen, sulfur, selenium, they're 2 electrons away from the full shell. So how many electrons will they gain? 2. What charge will they always take? Negative 2. Does that make sense? Great. And then nitrogen, phosphorus. What can you tell me about them? They have 3 what?
Away from.
Yeah, they have 3 electrons shy of a full shell. So what will that mean for them?
-3.
They'll always take a charge of -3 when they form an ion. Does that make sense? Does that feel like review? That feels comfortable? We've done that before? Good. Don't be shy. Okay, so am I going too quick? Does everyone have that down? All right. So how does this actually work? Well, we're going to look at a case, a nice simple one. We're going to start with sodium and chlorine. Now, sodium has the chemical symbol Na, and we're going to draw a Lewis diagram. Does anyone remember what a Lewis diagram is? Yeah?
And you have like the symbol, and then you only do the dots for the valence shell.
Very good. So we do the dots just for the valence shell. And sodium, how many electrons does it have in its outer shell? How many? 1. How'd you know that? You're right, of course. Good. So if you count over from the left on the periodic table, that tells you how many electrons in the outer shell. We look at sodium and count over, it's just 1. So I can draw sodium, and it's a happy little electron. Now, what did I ask you to react this with? Chlorine. How many electrons does it have in its outer shell? 7. Good. And as a rule of thumb, we put them on sort of in pairs on the compass rose. That's just good manners. Does everyone remember that? They've been shown how we tend to draw them. That rings a bell? Good. Now, sodium is a metal or a nonmetal? It's a metal. Does it have a low electronegativity or a high electronegativity? Low. Which means what? When I say sodium has a low electronegativity, it means what? Yeah. It means in a war, sodium is the French. You know what? We're cool. Take us over. Take our cities. We're fine. All right. Chlorine is a metal or non-metal? Non-metal. It has a low electronegativity or a high electronegativity. What do we think? High, which means what? Yeah, it's going to fight to the death for those electrons. So, in practice, sodium is going to lose its electron. So this has low electronegativity. This has high electronegativity. Sodium gives up its electron. Chlorine takes that electron. Now, that means sodium now has a cleared valence shell, which is good. Obviously, does it have a shell below that? Yes, but we still just show what was its valence shell, and we show that it's empty, which means that the shell below is now really the valence. And what charge did it take? Very good, positive. By the way, whenever we draw an ion with a Lewis structure, we put those square brackets around it. That tells us it's an ion, that it has a charge. And then we write the charge itself. How am I going to draw chlorine? How am I going to draw chlorine? Okay, but its valence shell is now full. And I'm going to keep that last electron blue, just so we know where it came from. And now, because they are both charged, and because their charges are opposite, what happens to them? What happens to two things that have opposite charges? They're attracted to each other. Does that make sense? That's a very strong bond. A positive electrical charge and a negative electrical charge have a strong force of attraction to each other, and we call that an ionic bond. So they are held together by their opposite electrical charges. Right? And we call that an ionic bond. That's all an ionic bond is. It's that you've made a positively charged ion, you've made a negatively charged ion, and they're going to be attracted to one another because they have opposite charges. Any questions about that? How would we name this? What's this thing called? What do we call it? What do we call it?
Sodium chloride.
Sodium chloride. Good. So this would be called sodium. And obviously sodium is just the name of the, the cation, the metal. Good. And chloride comes from what, obviously? Chlorine. But how's it been changed? So this is just the name of the cation. This is the name of the anion. But what did we have to do with it?
You changed the INE to IDE.
Good. We change it to the "ide" ending. "Ide" tells us that it's a simple binary compound. That's a simple ionic compound between a metal and non-metal. So whenever you see something ending in "ide," you know it's just going to be a binary compound. It's going to be a metal and a non-metal. If it's ionic. We'll talk about covalent later. Yeah.
What if it was like two metals or two gases?
We're going to talk about that. We will talk about that, but not today. So this would be sodium chloride. Does that feel like review? Feel like you've done that 1,000,007 times before? Okay. Well, let's do the same thing again, this time with magnesium and with fluorine. Okay, let's do that. So I want you to draw a Lewis structure for magnesium and a Lewis structure for fluorine. Go ahead and do that. Yeah. No problem. Magnesium is right here, and fluorine is right there. So Mg and F. Very good. So magnesium has 2 electrons, and fluorine has how many? 7. Good. Okay. What is going to happen here? Good. So this electron is going to go there. Now, what will now be true about fluorine? Which means what? You're right. It has a full valence shell, which means it's stable. It's happy. Is fluorine going to want another electron? But magnesium still has one. Is magnesium stable and happy? What do we have to do? How? All I have, you could do that, but all I have here is magnesium and fluorine. So what am I going to do? Yes. Brilliant. That's exactly right. We are going to add another fluorine atom. I put it to the left. It doesn't matter where you put it, by the way. So don't stress out if you had not left room to the left. You can put it below. You can put it above. You can put it on the other side. It does not matter. And now, what will magnesium do? After it does what? And gives it to this fluorine. Good. So how would I draw this below? What are the final Lewis structures going to be for these things? Let's start with this fluorine over here. What's it going to look like? Yeah? Do you have the answer? No problem. How am I going to draw this? What do we think? Okay. Great. Yeah, in square brackets. And what do I need to make sure I put on it? Yeah, it has a -1 charge. By the way, the 1 is really superfluous. You don't have to draw the 1. If we see a negative sign and no number, we assume it's a 1. Sometimes I will put a 1, sometimes I won't. There's no magic to that. Great, so that takes care of the fluorine. Is this other fluorine going to look the same? Yep. Great. What about the magnesium? How am I going to draw it? -2? +2. Got it. That's okay. I'm not offended. Yet. Good. So now, if this is to work, the charges have to balance out. Do the charges, I have -1 here, I have +2 here, and I have -1 there. What does that all add up to? It adds up to 0. So that's good. Now, what would we call this? Very good. The less common spelling of magnesium without an A, we would call it magnesium fluoride. Remember that the IDE, IDE, tells me that it's an ionic compound, a binary compound. And what would its chemical formula be? How would I write this in chemical formula?
MgF2.
Very good. Mg, F, and where does that 2 go? The bottom. Good. Does that make sense? In fact, we could say like 2 fluorine plus 1 magnesium gives us MgF2. You don't have to put that, but does that make sense? We took 2 fluorine atoms, 1 magnesium atom, and together we made magnesium fluoride. Now again, don't be shy, because I know for some of you it's been a whole year. I know for some of you it's been 2 whole years since you've had to think about this. Assuming you thought about it in the first place. You might have just blindly copied it in your notes. I don't know. I wasn't there. But does that feel comfortable? Does that make sense? Does it feel like review, or does it feel new and fresh? Review, I hope. Again, if not, don't be shy about that. Now, every time we want to do one of these, are we going to have to draw a Lewis diagram like this? I'll tell you, it would be a long damn semester, wouldn't it? If every single time we had to draw Lewis structures. So can we do this without drawing them? Obviously, since I'm asking, the answer is yes. Okay, so let's go through a couple examples, and then I can leave you to work on this on your own. But calcium phosphide, let's look at the next page. Calcium phosphide. In this case, what is the anion? What's the anion in calcium phosphide? Phosphorus, good. And what's the chemical symbol for phosphorus? P, very good. And what is the cation? Calcium, and its chemical symbol is Ca. Very good. Now, just by looking at the periodic table, you should be able to tell what charges these take. If we need to cheat, we can, because I gave you that chart on the first page that gives you all of the charges. See if you can do it just looking at the table. Let's give you these at the beginning of class. These are just cute, by the way, the nice ones. Got lots of information. So what charge will a calcium ion always take? Calcium ion always. I know I even have a bunch of them. Isn't that nice of me? Yeah. Yeah, don't worry about that. So calcium. Calcium, what charge is it going to take? Yeah. Two. How did you know that? You are, of course, right. There it is. Very good. It's in the second group. If you look at your periodic table, it's in period 4, and it's in the second column. It's in the second row, which means it has 2 electrons to lose. Does that make sense? So calcium is going to take a charge of +2. What about phosphorus? How many electrons does it have to gain before it has a full shell? 3. If you look, it's 3 back from the end of its row, right? It's 3 away from a full shell. So its charge will be -3. Good. Now listen, that skill of being able to look at a periodic table and quickly know what charge it will take is important. And you're going to get a lot of practice, I promise. So now, yes?
I just want to ask one thing. What's the oxidation phase for phosphorus? 3, 4, and 5. Right?
Yep. So in fact, it says ±3, 4, and 5. This is very, very, very detailed. More detailed than you need, which is good. I want this to have more information than we need. Under extreme conditions, phosphorus can be made to take different charges. But we're not talking about extreme conditions. We're talking about normal conditions. Does that make sense? So we can do a lot to elements if we put them under extreme pressure or extreme temperatures or things like that. For the purpose of this course, we're going to talk about basic chemistry, not exceptional chemistry. Does that make sense? Is that a fair answer? Okay. Now the question is this. Without drawing Lewis structures, can I figure out how many of each of these I need to make this work? Well, for the whole thing to work, the charge has to be 0, has to be balanced. There has to be as much positive as negative, right? So let's take a look at this. Now, again, I'm going to draw a little table here that we will never draw again, but just to show you the thinking. I think so. Again, I will never draw this again, but let's just think of it this way. if I had 1 calcium, what would the positive charge be? Each calcium has a charge of, so if I had just 1 of them, its charge should be positive 2. If I had 2 of them, its charge would be positive 4. If I have 3 of them, its charge would be, and if I had 4 of them, positive 8. Does that make sense? I could keep going, but I'm going to stop at 4, because spoiler alert, the answer is less than 4. If I had 1 phosphorus, what would its charge be? Negative 3. If I had 2 of them, what would its charge be? If I had 3 of them? And if I had 4 of them? Minus 12. Okay. Now the question is, how many of each of these do I need so that the charges can cancel?
3 calcium and 2 phosphorus.
Very good. If I have 3 calcium, that gives me a charge of positive 6. If I have 2 phosphorus, that gives me a charge of negative 6. And those charges cancel one another out. Does that make sense? You may have learned this in grade 10 as the crisscross rule, cross the numbers down and reduce the lowest terms. You're welcome to do that. I avoid teaching it that way because I think it teaches a trick rather than teaching the understanding. And I think it's important to understand it, not just to know the trick. Yeah.
Couldn't you just also multiply those things?
You can always multiply the numbers together. That won't give you the lowest terms, right? Necessarily. And the next example will show you that. Now, we're not going to necessarily draw this out every time, though it never hurts to. When in doubt, draw a chart. Not going to hurt you. But so the answer would be that we need how many calciums? 3 of them. And how many phosphoruses? 2 of them. Okay? Don't be shy. Does anyone not get what I'm doing with this? So anyone who looks at that and goes, what is Orlando doing? That son of a gun, I hate him. Or maybe minus the hate part. Maybe you're like, that Orlando, I love him.
Hate part.
No, I don't want to know about just the hate part. I like to assume that you all love me. It makes me feel good. So with that in mind, really what we found here was the lowest common multiple of these 2 numbers, right? Does that make sense? We had to find the lowest common multiple of those 2 numbers and then see how many of each of those we needed to get. Does it happen that 9 times out of 10, this number becomes that number and that number becomes that number? The crisscross rule you may have learned in grade 10? Yeah, but I want to make sure we understand it. Okay? With that in mind, can you try sodium oxide? Sodium oxide.
Like the compound name.
Sorry?
Like the compound name.
No!
No, I don't. Yeah, I kind of finished. So I went to the side. I never did,
Oh, no.
but I don't know.
Oh, no, I copied the wrong one onto there.
Yeah, I was gonna say I don't know how.
That's okay. We'll come back to it.
So we don't have homework.
We're going to have homework. I'm just going to have to print it for you. I can't believe I did that. This is why we don't make notes late at night, honestly. I gave you tomorrow's homework today.
What if we do it today?
That's not going to happen. Okay. So for this one, it's okay. I can throw homework together in 3 minutes flat. Stick it on the board. It'll be your job to do it. So for this one, how do we approach it? What should I do? What charge does sodium take? +1. And what's the symbol for sodium again? Very good. And what about oxide? Oxide is telling me that the anion is? Oxygen. And what charge does it take? Very good. So now, if every sodium has a charge of +1 and every oxygen has a charge of -2, how do we balance those out? If I had just 1 sodium and 1 oxygen, is that balanced? No. What do I need more of? Sodium. Specifically, how many of them do I need? 2. Does that make sense? If I wanted to draw the chart, again, it's not my expectation that you will do this every time or ever, but I just want to show why it works. Again, I don't just want to teach you tricks. I want to make sure we know why things work. If I have 1 sodium, that's a +1 charge. 2 of them, that's +2. 3 of them, that's +3. If I have 1 oxygen, that's -2. 2 of them, -4. 3 of them, -6. What's the easiest way to make this balance? Well, 1 oxygen and 2 sodiums. They cancel each other out. Are there different ratios that I could use? Could I say 4 and 2? Sure, it wouldn't be wrong. It just wouldn't be the simplest answer. Does that make sense? And for the purpose of this, we always view the correct answer as the simplest answer that gives you a charge balance. Now, I would rather see you say Na4O2 than Na3O7. At least Na4O2 would be balanced, but the best answer is both balanced and in lowest terms. Does that make sense? Yeah.
So it's like what you can.
It's exactly like working with fractions. The same principle applies. The same way we find lowest terms for adding and subtracting, lowest common denominators for adding and subtracting fractions is the way we do this.
So if you get like the largest point you or something like that, you don't have to include what you know with fractions and
Good. Yes. Now, do I need to put a 1 here? No. The rule of thumb is if there's no number there, we assume that the number is 1. All right? And maybe in grade 10, we were lenient with that, and we'd say, well, if you put the 1, I'll give you the mark anyway. In grade 11, I'm not lenient on that, okay? 1 is not only unnecessary, but it'll be deemed incorrect. It's kind of bad manners. Does that make sense? You'll get some of the marks. It shows me that you understand what you're doing. But part of science, too, is like the formality of it, the way we teach it. Does that make sense? Okay. So the name sodium oxide is Na2O. I want you to go ahead and try and do the whole sheet here. Go all your way through it. If you have any questions, don't be shy. Ask for help. And I'm going to find your proper homework file. I can't believe I did that. You know, if I just had textbooks. Yes.
My rule still works. Why do you say that?
Your rule totally works. You just have to make sure you know that if you have like BE, which is 2+, and O, which is 2-, that you understand that that can be reduced to just 1 of each. And as long as you know that, your rule is
So I know
golden.
there's 1 of each, you just write them side by side, there's no 1.
Yep, that's right.